Yo, yo, what up, math nerds? What's going on? Happy Thursday. I was a little late today, and I think I'm only going to be on for like maybe 35, maybe 40 minutes, because I do have to leave at 4, but I just wanted to still come on here and review some trig substitution stuff. How's everyone doing today? How's everyone's Thursday going? All right. I'm on here now. So as I mentioned today, we're just going to do some trig practice. I have a couple students that are also taking a trig class, a pre-cal class, really, and they're reviewing these types of problems. So I think it's kind of nice to see if everyone else is kind of going through the same thing. So these are the types of problems that I'm going to kind of review in the very beginning. I'm pulling these problems from a practice final from like some college class. But anyway, from here, if we have cosecant of 5 pi over 4, this is where you have to remember the unit circle. I don't know how many times I have mentioned here and have emphasized to remember and memorize the unit circle. So 5 pi over 4 is on this side, and it has the coordinates negative root 2 over 2, comma negative root 2 over 2. And cosecant is the reciprocal of sine. So cosecant of 5 pi over 4 is going to equal to 1 over sine of 5 pi over 4. And sine is always going to be the y value of that coordinate. So then we're just going to have 1 over negative root 2 over 2, which becomes negative 2 over root 2. Now this is the point where some people just don't care if we have radicals on the bottom. Some teachers don't, some teachers do. So if you have one of those teachers that hate radicals on the bottom, just make sure to multiply the top and the bottom by the conjugate. So that's negative 2 root 2 over, the bottom just becomes 2, and those radicals cancel out. Easy. Okay, this is just a warm-up. This was a part of a problem that we have, and then now here we go. So it looks like we have a triangle here, a right triangle, and this is 6 meters on the bottom here, and it looks like the angle is going to be 60 degrees. And what they want us to find is this value x. And we're going to end up finding all the other sides. So we have x as the top, and then we have y on the bottom. I know it's not conventional to do x and y, but, you know, why not? Okay, so for this one, most people like to use special right triangles. I'm literally just going to start using I'm going to set it up using SOHCAHTOA. We don't have to worry about special right triangles today, or at least not right now. And when we want to solve for x, we're going to go ahead and figure out which equation we have to use. Well, we have the x, which is the opposite, and then we have the 6, which is the adjacent. So which one of the three SOHCAHTOA uses opposite and adjacent? That's tangent. So we have tangent of 60 degrees equals x over 6. And this is where those special right triangles come in. You can remember the special right triangles here, but on the left side, tangent of 60, that's going to be root 3 over 2 over 1/2, which is equal to x over 6. The left side, you'll see that that just cancels out or simplifies to root 3 is equal to x over 6. And we're going to multiply that 6 to the other side. 6 root 3 is equal to x. Okay, so now we have that x value. All right. And for those people that are just tuning in on this live, typically I do Tuesdays. It's a integration bee. Thursdays, it's going to be some generic or general practice. In this case, I chose trigonometry. And tomorrow, Friday, it's going to be off trail. So we are going to do all kinds of problems. I have some crazy integrals that I'm going to try out. Don't know the solutions of them, but I'm just going to practice them with y'all. So keep in mind, continue to follow me and be on the lookout Tuesdays, Thursdays, and Fridays here at 3 o'clock. All right, let's try the next problem. Oh, shoot. I just realized we didn't solve for y. Never mind. Okay, so we have the value of x. I'm curious how we will solve the value of y. We can use either SOHCAHTOA or we can use Pythagorean theorem. Anyone in the chat knows how to solve that? Let's go ahead and do it. Yo. Someone said 12. It is going to be 12. Thank you, user 5919. Yes, and the reason why it's going to be 12 is because they used, I'm assuming, special right triangles. If not, they use Pythagorean theorem, but you're going to arrive at the same answer. How do we get that? There's a few ways we can use special right triangles. I'm going to use Pythagorean theorem just to kind of show everyone how this becomes 12. So 6 squared plus 6 root 3 squared is equal to the hypotenuse squared, which is going to be y squared. And now we have 36 plus, we have 36 times 3 is equal to y squared. And 36 times 3 is 108, which is equal to y squared. And then we get 144 on the left side. We take the square root, and we get 12. And that's probably not how user solved it, but someone would have used cosine. Some people would have used other values or special right triangles. I'm assuming that's what you used. So it's kind of fun, and it's neat to know that there's many different ways that we can solve stuff like this. Okay, this one's interesting. This is a problem that everyone learns: sine, cosine, tangent. They learn their trig functions, and then they arrive at a problem like this. We're going to have a coordinate, -4 comma root 3. And they're saying that this represents an angle. I guess it's drawn this way. And they want you to find sine of theta, cosine of theta, and they want us to find tangent of theta. So in the chat, who can give me a clue as to how we can start this? Well, let's go ahead and draw out a triangle here. So on that third quadrant, I'm going to draw out a right triangle. Okay, the -4 is actually going to be this top side because that represents the x value, and the root 3 is going to be this the vertical side. And we're going to find the hypotenuse, or the length of this segment, by Pythagorean theorem. So we're going to do -4 squared plus root 3 squared is equal to, let's just use c squared. So we have 16 plus 3 is equal to c squared. 19 is equal to c, and that tells us that root 9 is equal to c. So we have the hypotenuse there. And then from there, they're going to ask us, again, they want us to find sine, cosine of tangent. Well, looking at the triangle, keep in mind, sine is opposite over adjacent. I said opposite over adjacent. Opposite over hypotenuse. I'm sorry. So that means that sine is going to be the opposite, which is root 3, over the hypotenuse, which is root 19. I would definitely, Gadero or Cade Robinson, I'm assuming, thoughts on taking calculus junior year or high school. I would definitely, suggest that you take it in high school. I think it's, a good opportunity for you to do it if that is presented to you. I took it as a junior in high school. Some people take it as early as a sophomore. But if you can take it in high school, regardless whether it's junior or senior year, I would highly suggest it. All right, going to cosine. Cosine is adjacent over hypotenuse, and that's going to be -4 over root 19. And then we have the last one, which is tangent. Tangent is going to be opposite over adjacent. And the opposite was root 3. The adjacent was -4. So now we have our three values. This was presented to me by a student. He takes pre-calc, and we were doing, we were discussing his test, and he said there was this one problem that I didn't understand, and it was this particular problem where they give you the point in the coordinate system, and you got to be able to find the sine, cosine, and the tangent values. All right, I think now we can kind of start getting to some more interesting stuff. So again, I'm pulling this from a test that's a pre-calculus college level class, and they want us to prove this identity. Secant theta is equal to cosine theta cotangent squared of pi over 2 minus theta, and then plus cosine of negative theta. Okay, I'm curious, because there's not that many people in the chat today. Typically, there's a lot more because I typically do integrals and all that. But I'm curious what you guys are learning now. If you guys know how to solve this, any suggestions? So whenever we're trying to prove identities, they always suggest that we should definitely formula chart. Yes, I think we're going to use that. They always suggest that you pick and choose which side looks the most difficult. And then from there, we're going to start rewriting stuff. Yes, so I agree. Kevin said get rid of the phase shift. I think we're going to do that. Okay? So we're going to work on the right side. So we're going to leave the left side on its own. Secant theta is equal to, the first thing that I'm going to change is this cosine of negative theta. Cosine of negative theta is equal to something. Can anyone tell me what that is? Aaron, the phase shift is things like the pi over 2 inside or the negative theta that we have inside the cosine. I wouldn't necessarily call that a phase shift, actually. The phase shift is just going to be the pi over 2. So whenever the things being added together, added or subtracted inside the parentheses, that is going to be the phase shift. Yes. So everyone's saying that, or the chat's saying that it's going to be cosine. That is correct. So that last part is just going to become cosine of theta. Reason being is because cosine is an even function. So whether we put a negative inside, it's just going to be the same value. And I guess as a little bonus, keep in mind that sine of negative x is equal to negative sine x. So that's going to be a odd function. Okay, so let's continue. It looks good so far. I think the next thing that we should try to change is this cotangent squared of pi over 2 minus theta. I'm assuming that was the one problem or the one identity that they wanted everyone to remember. I actually don't remember that one. So if someone in the chat knows, go ahead and tell me. But otherwise, I'm just going to look it up. So trig identities. The power of Google, guys. We can just literally look up a lot of these things. So sum and difference. Let me just look this up real quick. Again, we're trying to find the identity for cotangent squared of pi over 2 minus theta, which I actually do not remember. Unless someone has a different idea or a different method that we can use. Let's look that up. Okay, I have a few over here. Yo. Things are not looking too good. Ah, 1 minus tan squared of pi. Is that true? Oh, so obviously we're changing it. I see. All right, let's go ahead and start with that. Duh. Okay, so they're saying, chat's saying that we're going to convert this into 1 over tan squared of pi over 2 minus theta, because that is not even, well, I guess you can say it's a trig identity, but cotangent is just a reciprocal of tangent. So we're going to start off with that. Okay, and then now that we fix that, we still need to somehow find this tan squared of pi over 2 minus theta. Now we know one of them. Jeez. Tan squared. Okay, so this is what I'm getting. This is what I'm gonna use. I don't want to rewrite this, but I guess we're just gonna go ahead and do it. Or yeah, I changed it to cosine and sine. Didn't want to go there, but it looks like that's maybe the whole point. Let's go ahead and do that. So we're gonna go one level further, and we're gonna change that tangent into sine squared pi over 2 minus theta over cosine squared pi over 2 minus theta, and then plus cosine theta still. And that changes to this, cosine theta times cosine squared pi over 2 minus theta over sine squared of pi over 2 minus theta, and then still plus cosine theta. You know what? I can't pull the square out because the square is part of it. That's like saying this is sine times sine, unfortunately. Okay, so it's looking better. The whole idea is we want to turn this into sines and cosines. I'm looking at the identities, and I want to choose. I know this is a sum and difference, but I don't want to commit to changing everything. I guess we're just going to have to do it. We are going to, let me just create some space on the blackboard here, but what we're going to do is not only am I going to make this a little smaller, but we're going to change that cosine and the sine, and we're going to use the sum of difference rules and then multiply everything out, okay? So this is what I mean by that. So we're going to do secant theta is equal to cosine theta times, and then for this one, I'm first just going to use the sum of difference formula for cosine and do cosine pi over 2 cosine theta minus, or this is going to be a plus, sine pi over 2 sine theta, and this whole thing is squared, over, now I'm going to do the same thing for sine. This is going to be sine pi over 2 cosine theta minus cosine pi over 2 sine theta squared plus cosine theta. Yo, do you guys see that? Let me highlight what I'm looking at. I'm talking about this cosine of pi over 2, this sine of pi over 2, sine of pi over 2, and cosine of pi over 2. That's real nice. Okay, so in the chat, you look at the circle and there's your answer. Yep, absolutely. I agree. I'm just going to call you bald. All right, guys, cosine of pi over 2. I'm trying to simplify that. Who can tell me what that is? Cosine of pi over 2. So I want to simplify that first part. Cosine of pi over 2 in the chat. Who can let me know what that is? Yo, cosine of pi over 2, that's going to be 0. So we're definitely going to change that into a 0. So that one, the cosine of theta, because that's 0, that entire section cancels out. Okay, now we go to the next one. Now we're looking for sine of pi over 2. What is that equal to? Nice. Someone said 1. That's exactly what it is. So this whole thing is equal to 1, which is really nice. So on the bottom, sine, that first part, sine of theta, is also equal to 1. And then that second part, cosine of theta, is equal to 0, so that cancels out. Yo, that's going to help us out so much. Because look, let me go ahead and rewrite this. We still have secant theta is equal to cosine theta. And then all we have on top is just sine theta squared over, and on the bottom, all we have is cosine theta squared. And then the whole thing plus cosine. I have a really good feeling about this. Okay, let me go ahead and continue to make this a little smaller. And looking at that, what do you guys think is going to happen? Something's going to cancel out. Let's see if you guys can tell me in the chat what cancels out here. Whoops. Whoops. Meant to make this smaller. Did not work. Failed. Hold on. Let's choose a different spot. There you go. Much better. Yes, so someone said cancel out one of the cosines. They are absolutely correct. In this section here, this cosine cancels out with one of the cosines on top. And that's super helpful because now we have sine square theta over cosine theta plus cosine theta. Dude, this is beautiful because now we can use the graph, but the whole point is to identify these things. We have two fractions being added together. We're going to add them together by getting common denominators. So I want to have the same denominator on that second fraction. So I should multiply, something by the top and the bottom. So I'm just going to multiply by cosine over cosine. And so I get secant theta is equal to, check this out, we're just going to put everything under the same denominator. So plus that second part becomes cosine square theta all over cosine theta. Oh my goodness, we did it. Hold on, let me shrink this one more time, just a tiny bit, guys. All right, on top, do you guys recognize that? Sine squared plus cosine squared? Yes. Jorge said top is equal to 1. That is 100% correct. Sine squared plus cosine squared, that is one of the universal trig identities that we should know. And then we have secant theta is equal to 1 over cosine. And that's the same thing as just secant theta is equal to secant theta, because remember, secant theta is just a reciprocal of cosine. Boom, we proved it. What's up? Yes. Reciprocal identity, clutch champ. Yes. 100%. God, this was beautiful. At first, it looked daunting, but we just have to break it down one at a time. And I think that just goes to show with these identities is that you have to take it one step at a time. Okay. Let's see how much time we got. We still got some time. Oh, this is great. All right, so check this one out. I kind of did a problem like this yesterday. I did a video on it. And the reason why I'm doing trig is not only are students, needing help on it, but for the most part, I see a lot of videos of mine that are pre-calculated that are being viewed. So it looks like we got to give the people what they want. Okay, so I have this trig equation, and they want you to find all solutions. Mario, the algorithm knows. If we finish this one quick, I'll try to do another identity. Okay, guys, so we're solving trig equations. What should be the very first thing that we do? Since this is set equal to 0, we got to do something. Someone said subtract. Yeah, but so we can subtract both sides? Interesting. Okay. So with problems like this, because they're set equal to 0, they are set beautifully for us. They are ready to go. What I mean by that is all we need to do is some magic of like factoring stuff. And then you're going to see, because this whole thing is equal to 0, it's really going to benefit us. Okay? Substitute sine of 2x. Paul, I can try that, but I'm going to show you the first thing that I'm going to do. Maybe once I do this, everyone's going to be able to see what I'm doing or what this means. Okay. So do you notice that both terms have a cosine in common? Why not factor that out? And what am I left with now? I have 1 minus root 2 sine of 2x is equal to 0. Look at that. The reason why I said this is because you have two things being multiplied together. Let's go ahead and color this in a different one. Let's do this in blue. You have two things being multiplied together. And this is what we're going to use the zero product property. When two things are being multiplied together and they equal to 0, either one of them or both of them are going to equal to 0. And then Jorge said that's exactly what we should do. Set them equal to 0. So we're going to set the first one up. We're going to set up cosine x is equal to 0. And then we're going to set the other one up. 1 minus root 2 sine of 2x is equal to 0. Sham God, thanks for the follow. Okay, so cosine of x is equal to 0. We need to remember our unit circle. Where does cosine of x equal to 0? I'll tell you two things. It is in two different radians. But don't forget we want all solutions. But let's just start off with the solutions in the unit circle that we know of. Where does cosine of 0 equal, or cosine of x equal to 0? Someone said 90 pi over 2. Yup, 90 degrees. Yup. Nice. So a lot of people like their degrees. I personally like radians, so I'm going to keep it as radians. 90, Sam, cosine of 0 is 1, and then cosine of 180 is -1. So don't forget that. I think you're thinking of sine. So yes, it's going to be 90 and pi and 270 degrees. So if we're looking at the unit circle, let's draw it in yellow. I'm sorry. Okay, if we're looking at the unit circle, cosine is 0 and pi over 2, and then 3 pi over 2. So these are our solutions, but then don't forget, we want all solutions, meaning that if we were going on an interval, if we were going on the circle, we want to be touching these every single time. So the way my solutions are going to be set is x is equal to pi over 2 plus, check this out, pi n. Brandon said 2k pi, and that technically is true. But Brandon, notice that I'm combining both of them together. Oh, people want k. Let me just change it up. Pi k. So I'm combining these together because if I start at pi over 2, if I move, whoops, I'm erasing stuff. I didn't want to erase it there. If I move from pi over 2, oh, there's like something showing up there. This is what I get for doing this. Hold on, let's erase this part. There you go. Okay, so if I start at pi over 2, once again, if I move pi units, I get to that 3 pi over 2. And if I go pi units again, I get to that other pi over 2. And I can do that multiple times. You could do the 2 pi k. Fuzzy Balls, how'd it go? I hope it went well. So you could do the 2 pi k, but then you still have to include the 3 pi over 2. So typically, this is the more condensed answer. Okay? Let's talk about that second part, the 1 minus root 2 sine of 2x. We need to set it equal to 0, or it's already set equal to 0. So we're going to subtract the 1 to the other side. And then we're going to divide by negative root 2. Yo, this doesn't look like anything we've seen on the integral, right? Or on the unit circle. Sorry, I was reading Fuzzy Ball's comment at the same time. Someone said double angle, technically, and this is going to be a double angle, and I'll show you how we're going to change that real quick. Okay, 1 over root 2. Oh, yeah, negative, Jorge, it's positive because it was negative 1 on the right side, then I divided by a negative root 2, and so it's going to make it a positive. Yep, there you go. Yeah, it's always good to talk amongst yourselves and be like, oh, shoot, never mind, it was the other way around. 1 over root 2. This is, if we multiply both the top and the bottom by the radical, or by the conjugate, not the radical, I'm sorry, by the conjugate, we are going to get root 2 over 2. So really, sine of 2x is equal to root 2 over 2. And then Benjamin is saying pi over 4. Let's talk about that real quick. Let's not worry about the 2x just yet, okay? We're going to leave it. Let's just pretend that this is sine of theta is equal to root 2 over 2. So where in the unit circle does sine equal to root 2 over 2? There are two solutions here. Let me erase this so I can draw my unit circle. Okay, as I'm writing this, let me know in the chat. So someone said pi over 4. Pi over 4. Oh, yeah. So Benjamin, pi over 8, we'll talk about how we're going to get there. You're already ahead of the game. Pi over 4, 45 degrees. So that's definitely 1. And there's another, guys. Clutch said 3 pi over 4. Yes, sir. Let's go. So 3 pi over 4 is going to be the other one. And this one, if Brandon, you're still here, this is where we're going to use the 2 pi k. Because we can use the pi because we're not going pi units from one to the other. So check this out. Remember what I said. We're still not focused on 2x. We're just doing theta is equal to pi over 4 plus 2 pi k. And then theta is equal to 3 pi over 4 plus 2 pi k. Let me just make some space in the blackboard. This will be our grand finale for this problem. And then I'll mention how someone, I think it was Benjamin, was already ahead of the game and said, oh, it's going to be pi over 8. But I'll talk about why that's the case. Okay. So let's just make this a little smaller. Okay. We're good. There you go. Okay. So remember, all we've done so far, our solutions were from the cosine one. So we have x is equal to pi over 2 plus pi k. We know that's one solution. The other one, remember we had said we had theta. But now we're going to say 2x is equal to pi over 4 plus 2 pi k. And then 2x is equal to 3 pi over 4 plus 2 pi k. And then now we're going to go ahead and divide everything by 2. Divide by 2, divide by 2. Divide by 2, divide by 2, and divide everything by 2. Okay, for that first one, x is equal to pi over 4 divided by 2 is pi over 8. This is where Benjamin was already thinking of pi over 8. And then plus, notice that second part, the 2 pi k divided by 2 becomes just pi k. And then now we have our other solutions, 3 pi over 8. And that's just going to be plus pi k. We got it, guys. We got it. We got it. So the whole point of these problems, whenever you have trig equations, always set it equal to 0. And then just mess around with these things, okay? Pi k, yes. Pi k. All right. I think I have time for one more problem. I know today was a short one, but again, follow me on here. Follow me on Instagram and TikTok, or TikTok and YouTube. I post different content in different socials. But tomorrow, I am gonna start doing some like integration with like some different substitution, like the Weierstrass substitution. I don't even know what it's called, but give me a follow, guys. Okay, so let's try to do one more. Let's go ahead and prove trig identity. Okay, and as I am looking for this, guys, just a reminder, I go live on YouTube every Monday. I go live on TikTok Tuesday, Thursdays, and Fridays. So around the same time. But of course, if you can't catch the live, then just go on YouTube where I post all the replays in case you guys want to review stuff. All right, let's go ahead and do... Yeah, there's like some good ones. Some easy ones, I would say. Okay, so we have secant x sine of x is equal to, or over, I'm sorry, tan x plus cotangent x is equal to sine squared x. And the prompt is to prove the identity. Okay. Moby, k, back to that problem. The k represented, we're going this many pi units around the circle. So if it was like pi k, means it could be 1 pi, it could be 2 pi, it could be 3 pi. So that's how many revolutions we're going, or that's how many 180 rotations we're going around the unit circle. All right, guys, so we're going to go ahead and prove this. I don't have a pre-calc playlist on YouTube, but if you guys want specific things that you want to review, email me or drop it somewhere in the comments or somewhere on my YouTube channel. Just comment on that, like, hey, can we review XYZ? And I'll try to make a video for you guys, okay? Oh, Benjamin, thanks for the cake. All right, so someone said combine secant and sine to tangent. Yes, so why are we going to do that? Oh, how are we going to do that? The very first thing that we're going to do is let's rewrite everything in sines and cosines, and then we'll talk about why. Yeah, so Jorge said switch everything to sine and cosine, and then someone had said, Keishan said combine secant and sine to tan. That's what we're going to do. Hopefully that helps us. So we're going to turn everything into sines and cosines. The secant becomes 1 over cosine x times sine over sine x over cosine x plus cosine x over sine x. Okay, and before we even turn this into the top into a tangent, let's just not do that just yet, because everything is kind of in sines and cosines. The right side is in terms of sine, so maybe we want to keep everything this way. Okay. Tyler, yes, they're amazing. Wallace Stem, everyone give that guy a follow. Give him some love. All right, everyone, what do you suggest? Jay, when you were talking about 2 pi and pi, you end up with negatives or positives, because k could be 0, 1, 2, 3, 4, 5, or negative 1, 2, 3, negative 1, negative 2, negative 3, negative 4. It can go in both directions. Okay, so someone said common denominator. I'm going with common denominator. So let's go to the bottom, the very bottom. And we're going to get a common denominator, which means I have to multiply the top and the bottom for that first fraction by sine, and the top and bottom for that second fraction by cosine. Okay, so let's rewrite this. So that top one just becomes sine x over cosine x, which is technically tangent. That might help us. We'll see in a little bit. But on the bottom, I have sine squared x over sine x, cosine x, plus cosine. Actually, let's put it all in the same denominator already. Plus cosine squared x over sine x plus cosine x, or sine x cosine x. Benjamin, thank you for the heart. Yeah, Moby, I agree. I think, you know what? I think it's going to be a tan. We'll change it if we need to, but you're right. People are identifying that the top looks like tangent. That's the case. That's true. There we go. So Paul said change that sine squared plus cosine squared into a 1. That is 100% what we should be doing. That is equal to 1, baby. Okay, so then I was a bad math writer there. I should put e is equal to sine squared. Okay, so now we have sine x over cosine x divided by 1 over sine x cosine x is equal to sine squared x. And this is where a ton of people get confused. Yo, it's not that hard. Okay, we have a fraction divided by a fraction. Let's think back in like 4th grade, maybe 5th grade, 7th grade. What happens when we divide two fractions? Keep, change, flip. So this is technically sine x over cosine x divided by 1 over sine x cosine x. Yo, which is the same thing as sine x over cosine x. Flip the sign, or change the sign, and then flip the fraction. You guys see something? Something that cancels out? Clutch, take the reciprocal. Yep, so we're doing, and then we're multiplying. Thank you, Caesar. The cosine. Clutch champ said the cosines cancel out. 100%. Boom. And so now what are we left with? On the left side, it's sine x times sine x. Those two signs multiply together. And that equals to sine squared x. That equals to the right side. Yo, we got it. We got it, chat. Oh, the comments won't let you see? Oh, my bad. I think you could like hide the comments, but look. I will make it smaller for you guys. I think that's going to be better. I think, guys, I'm so close to 20K, and I think by then TikTok is going to allow me to like stream on like OBS. Please, if you guys can, follow me. Tell your friends. I want to get to 20K because I want to be able to stream so that we won't be able to see this screen. Look, you can see my hand right here. I'm like literally filming a computer screen. I don't want that. It's going to be crisp. There's going to be some lo-fi music that we're going to be playing in the background. It's going to be sick. Okay? Anyway, so that was our last problem. A little short of a live today. But guys, tomorrow, if you guys are ready to hang out at 3 p.m., maybe like 2:40-ish, maybe a little earlier, I'm doing some crazy integrals. I'm going to try the Feynman technique, which I have yet to perfect. And then we're going to do some like, I keep forgetting what they're called, but I even saved it. It's like the Weierstrass substitution. We're going to do a bunch of problems with these. So if you guys are familiar with these, the Weierstrass substitution, just keep in mind that's exactly what we're going to do tomorrow, okay? It might be a train wreck. We might fail. But we can do this, okay? Oh, okay. Wallace said QED. Oh, no. Better yet, Tyler. Better yet. There, I'm done. All right, guys. So I'm going to end the stream. But again, follow me here. Follow me on Instagram, on YouTube. I'm trying to go live Mondays on YouTube, Tuesdays here, Thursdays here, and Fridays here. So I'll see you guys tomorrow. And I'm looking forward to it. It's going to be a train wreck, but let's just have some fun. All right, everyone, take it easy. I hope you have a great rest of your Thursday, and I'll see you soon. Ta-ta.